Good morning and good afternoon, everyone. It's a pleasure for me to introduce our invited speaker, Professor Sylwia Cichacz from AGH in Kraków in Poland. Professor Sylwia Cichacz, her research interest includes labeling of graphs and fault-tolerant system. And today she is going to talk about critical bipartite graphs, their properties and their application in a network of sensing and relay nodes to establish a topology of links between them. So,
thank you, Magda.
Your time.
Introduction. Thank you. It's a pleasure to be here. So I will have to now share my screen, but I don't know what to do. I could do that before. Okay. Okay, so this is a joint work, and we're still working on that with Agnieszka Gerlich and Karol Suchan. So I will start with definition which was given in 70s by Hayes. So we have a given graph H and a positive integer k, and we are looking for a graph G that is called k fault tolerant with respect to H if G minus S, where S is the set of vertices, contains a subgraph isomorphic to H for any subset such that the cardinality is at most k. So, for instance, if I have H is a path P6 and k is 1, then I'm looking for a graph such that if I delete one vertex from this graph, there always will be a path P6. And this is quite easy question because, of course, the cycle C7 is one fault tolerant with respect to P6, because if I delete any of its vertex, there always will be path P6. You can also see that this graph is not two-fold. It is not two-fold tolerant and with respect to P5, right? Because I can delete these two vertices and I don't have a path P5. So that was the question, and the motivation for that was an application. So suppose that we have a very complicated computer networks. Actually, I have to say that I asked AI to draw me a very complicated computer network, and it gives me that picture, and I really like that picture. So we have a very complicated computer network, and this network works only. Of course, there can be some mistakes, or some computers can be broken, and the network works only if it always has some preserved architecture. So suppose it can work only if there is always a cycle C, I don't know, 100, or if always you can join computers into pairs, and so on. So that was the motivation, and there were a few directions of that. So because of this application, one could think that we are looking for such G, which is k fault tolerant, such that we are looking among, saying, the graphs of order of H plus k. So I have exactly as many nodes as I need, and I'm looking for the networks that they have minimum size, so minimum number of edges. Maybe this is because the connections between the computers is very expensive, as well as the nodes. So I would like to have this network cheap, let's say, okay? And this direction was given by Hayes in his first work. I'm sorry. And then another direction is that we are looking for k fault tolerant graphs that they have relative small numbers of new vertices. Okay, so probably for sure there are more than k vertices, and relative small maximum degree. And this was studied by Along and Chang and Ueno and Yamada, and of course many others. And one other direction which is also interesting is that we are looking for graphs which have as few as possible edges. We don't care about the number of vertices. This is maybe the case when the computers are very cheap, but the connection between of them is very, very expensive. And it was also said by UNO and the others, and Andrzej Jacques and some other my colleagues from my universities. So during this talk, I would like to focus on the first direction. So I will be looking only for such k-fault tolerant graphs that they have as few as possible vertices, so the order of the graph h plus k, and minimum number of edges. And I said that maybe here in that computer network, we always want to join the computers into pairs. So so that the pair is connected between, that there's a connection between the pair. So what I'm looking for actually, this is a perfect matching in my graph G after deleting any of k vertices. And this is also known under the different name because we say that a graph G is called k-factor critical if after deleting any of k vertices, the remaining subgraph has always a perfect matching. So I have P7, and this P7, the problem was introduced by you in 1993 and independently by Favaron in 1996. So I can say that P7 is one factor critical. Why it is? Because if I delete any vertex, then always I can find a perfect matching. So always I can join, I can find the pairs of two computers connected, right? So if you look on that definition, it's quite easy to observe that if I have a bipartite graph, then a bipartite graph is not k-factor critical, right? Because I can delete vertices from the smaller partition set, and then for sure I won't have one factor in my graph. So now I will present the robust nurse assignment problem. So suppose that I have few nurses and I have few jobs that they need to do, but it's not that each nurse can do all jobs because maybe she's not educated in for doing all jobs, or you have maybe some different duties. So here I'm showing which nurse can do which job. And I have 3 jobs and 6 nurses. And of course, for some, money saving, it would be good if I have as few nurses as possible during the shift. So if on my shift I have those nurses, then of course I can do all the jobs because I would like to have all the jobs done, and one nurse can do only one job at the time. So I can give them such jobs, and then each job is done. But if I have those 3 nurses, then one can see that this job wouldn't be done. So that is a problem. And in formal notation, my input is a bipartite graph, and I have 2 sets, and one set is the set of job, and one set is the set of nurses. So my V will be the set of jobs, and U will be the set of nurses. And there is an edge in that bipartite graph if and only if the nurse V can do the work U. Okay? And the robust nurse assignment problem is find the maximal number of possible absent nurses on one shift such that each job is done. And once more, we assume that one nurse can do only one job. So here is the model of the previous situation. So I have 6 nurses and the connections between the works. So here are the nurses and here are the jobs. And as before, if I don't have those 3 nurses, then this job cannot be done, right? So this would be a problem. So I said that in general, there is no K-critical bipartite graph, but there is a definition of K-critical bipartite graphs. So a bipartite graph with the partition sets U and V is called K-critical, where K is the difference between the orders of the sets U and V, and it's called K-critical. It's after deleting any K vertices from the set U, so from the bigger set, the remaining subgraph has a perfect matching. And it was introduced by Lee and Ni in 2009. And one could see that this graph, which is here, is free critical. This is an example of critical graph. I don't have a problem like before. So before I proceed, I will give you one more definition. And the definition is about a perfect matching of V into U. So if I have a bipartite graph, then if every vertex in V is covered by some edge from a set M, then we say that this set M is a perfect matching from V and U. So here is an example of such a perfect matching. So what I'm looking for in my K-critical bipartite graphs, I'm looking for a perfect matching from V to U after deleting any of K vertices from the set U. And this is very well-known theorem of Hall. And it says that if I have a bipartite graph, then there exists a perfect matching of V into U, if and only if for every subset A, which is a subset of the set V, there is that the cardinality of this set is not bigger than the cardinality of the neighbors of the vertices from this set. And Laroche et al., they give very similar theorem, if and only if, for K-critical graphs. So if I have a bipartite graph U and U, V, and E, and K is a natural number, then the graph is K-critical, if and only if for every subset A from the set V, there is that the cardinality of A is not bigger than the cardinality of the neighbors of the set A minus K. So you see that if K is 0 here, I have Hall theorem. So I have a perfect matching from of V into U. Okay, so this is the example of my nurses, and if you look on that, then it's quite easy to see that if I would like, if I'm deleting three vertices from the set U, then it has to be that each vertex from the set V has to have at least 4 neighbors, because otherwise it will be I can find such a set S that it would be isolated after deleting this set. So here is an easy observation that if U is N and V is M, and I have this k, which is the difference between them, then if G is the bipartite graph is k critical, that the minimal degree of the vertices in the set V, so in that set, has to be at least k plus 1. K plus 1. Once more, if I have a vertex in the set V and the minimal degree is k, so it has exactly k vertices in the set U, then if I delete those vertices, this vertex would be isolated in the remaining graph. So for sure, I don't have a perfect matching. So because of that, and because in the set V, I have m vertices, I have that the number of edges in my graph G has to be at least k plus 1 times m. So because I would like to minimize the number of edges in my graph, because maybe, I don't know, maybe the workshops for the nurses is expensive, so well-educated nurses are very expensive. So I would like to minimize the number of those edges in my graph G. Here is a case when I have a complete bipartite graph, but this is not the case because, as I said, I would like to minimize the number of edges. What I can do, and this is by pigeonhole principle, I can obtain this graph, which is k critical, in such a way that I'm taking V vertices in the set U, and I'm joining those vertices with all vertices from the set V, and then the remaining vertices, for the remaining vertices, I'm just adding one edge. And for sure, this graph is also k critical. One can easily check that. Because if I delete these three vertices, then I have perfect matching. And if I delete, so I will erase that. If I delete like maybe this vertex and that vertex and that vertex, then I'm using those edge, and this vertex is joined with any vertex from the set V. So easily I can find perfect matching. But as I said, maybe the nurses who are well educated, they have a lot of possibilities to make the work. Maybe they are expensive. They want to have very high salary, or for some reason I would like to have that all nurses they are almost on the same, I would say, level of education. Okay, so what I would like to do, I would like to find here such a graph that none of the node in U is overloaded. So none of the node has too big maximum degree. And here is the case. And this graph is also k critical. It's pre-critical. So if I delete any vertices, three vertices from the set U, I can find a perfect matching in my remaining graph. And you could see that the degree of any vertex in the set U is as small as possible, because from that I have that 3 times 4 is 12. So this is the number of edges in my graph, and this is as small as possible. It cannot be smaller, right? So it means that if I have 6 vertices in the set U, then the smallest possible, the smallest biggest possible degree is 2. So this is the case, and this graph is critical, pre-critical. Okay, so what is my goal? Once more, no high degrees. So my question is it possible to distribute the edges equitably without overloading any of the node. So the problem, I have a given positive integers n and m, where n is the number of the vertices in the set U, so in the bigger set, so of the set of the nurses, and m is the number of vertices which is smaller, so m is the number of jobs, and bipartite K-critical design problem for n and m is to find a K-critical bipartite graph of order n plus m, which is K-critical and lexicographically minimum with the respect of maximum degree in the set U and maximum degree in the set V. So this is my goal. So, as I said, if this number, so once more, I have at least this number of edges, because in the set, I just want to make in the set V, I have m vertices, and in the set U, I have n vertices, and any vertex here has at least degree k plus 1. So possible minimum number of edges is m times k plus 1. So what is the smallest possible number, smallest possible maximum degree in the set U? This is m k plus 1 divided by n and the ceiling of this. Okay, so I will denote by a this number. And the first case is if a is a natural number. So that was the case of the example I showed you. So we are able to show that there exists an AK plus 1 regular bipartite graph. What does it mean, AK plus 1 regular bipartite graph? It means that in the set V, all vertices have degree A, so they all have degree A, and here in the set U, all vertices, they have degrees K plus 1. So I have only two possible degrees in my graph. But what is important, in one set, all degrees are I, and in the second set, all degrees are K plus 1. So there exists an A K plus 1 regular bipartite graph such that, sorry, I messed up. Here should be V and here should be U. Such that this bipartite graph is K critical. And we also were able to show that if A is integer, then there exists an AK plus 1 regular bipartite graph that is not K critical, if and only if A is strictly smaller than n minus 1. And the case where A is not a natural number was much more difficult. And what we were able to show together with Agnieszka, that if n and m there are natural numbers and k is the difference between them, then there exists a graph such that U has n vertices and the set V has m vertices, and the degree of U for any vertex from U is the floor or the ceiling of A. This is the floor of A, and this is the ceiling of A. And degree of V for any for any vertex from the set V is k plus 1. So that is our main result, and we just show the construction. The question is still open, but we could find something. The question is it possible to find such a graph, such that the degree of U is from this set, and the degree of V is k plus 1, that is not k critical. And for a very long time, we weren't able to find such graphs. But then we used bigraphic sequences. So what is a bigraphic sequence? So suppose that I have a sequence P in there's non-decreasing order and sequence Q, and there are both sequences of non-negative integers. And then the pair PQ is bigraphic if and only if there exists a simple bipartite graph G such that U is n, so the number of elements in the sequence P, and V is m, the number of vertices is m, so this is the number of the elements in the sequence Q. With P and Q that describes the degrees of the vertices U and V respectively. So this is similar problem of graphic sequences, and the algorithm how to find them is similar to the one for graphic sequences given by Havel and Hakimi. So what is the theorem and the algorithm? So the theorem says that the pair PQ is bigraphic if and only if the pair P prime and Q prime is bigraphic, where P prime and Q prime is obtained from P and Q by deleting the largest element P1 of P and subtracting 1 from each of the P1 largest elements of Q. So this is very similar algorithm to those given by Havel and Hakimi. So here is an example. I have n is 6, m is 5, and this is my P and Q. So what I'm doing. So I will delete this, and from the biggest elements of Q, I will maybe write it down, so it will be my two, 1 and 1, and this is my V1, V2, V3, V4, and V5, which are 2, 2, 2, 2, and 2. So what I'm doing, I'm deleting that and subtracting 1 from V1 and V2. So gives me such edges. So here will be 1 and 1, 2 and 2. And now what I'm doing, I'm sorting this sequence. So I will obtain 2, 2, 2, 1, 1. And this is for V3, V4, V5, V1, and V2. And I'm doing this procedure again. So I didn't call them, but I will do that. Okay, so now for U2. So U2, I join with V3 and V4. And I subtract 1, so I will get that sequence. So I'm sorting this again. I won't write it, but now for U3, I'm joined with V5 and V1. So here will be 1, here will be 0, 1, 1, 1. I'm joining now V4 with V2 and V3. Right? And now V2 and V3. So I'm left with 1, 1. Here is 0 and 0. And V5, U5, I join with V4. And U6, I join with 5. So this is one example. And the second example is I can just do it for the sequence QP, not PQ, but QP, and I will obtain another graph. So maybe I will do that. 2, 2, 2, 2, 2, and this is for my 1, 2, 3, 4, maybe 5, and here will be 2, 2, 2, 2, 2, 1, 1. I'm sorry, I have too many twos. U1, U2, U3, U4, U5, U6. And now what I will obtain will be such a graph. Missed one word. So those graphs are not isomorphic, and actually you can easily see that the second one, if I delete like this vertex, and let's say this vertex, is not okay, is not sorry, that I didn't want to delete. I just want to show that they are not isomorphic because this graph is not connected, whereas this graph is connected. So this is the difference between these two algorithms. It's one. Oh, I don't know what happened. Sorry. It's my pen. So this is we use the difference between using the sequence P, Q, and QP, and we obtained the following theorem. So if I have two positive integers, such that the greatest common divisor of them is C, then if the one of the conditions holds, like this C is at least 2 and k plus 1 is smaller than k, or k plus 1 divides n, then there exists a graph G such that U is n and V is m, and the degrees is in the ceiling of A or floor of A, and they are not k critical. But you see that this is not full characterization of not k critical bipartite graphs with degrees like that. Okay, another problem that we considered for k critical bipartite graphs was connectivity of this graph. So it was shown by Favaron in his paper where he introduced this problem, that every k-factor critical graph is k-connected. And Lee and Lee, they proved that a bipartite graph is k-critical, then it has to be connected. And it's quite easy to see that it has to be true, because if I have a bipartite graph with two components of connectivity, let's say, like this, then one can easily see that if I delete, like, let's say, k vertices from this, then it can happen that probably I won't have a perfect matching, or maybe from this. So connectivity is really really necessary. What we were able to prove, maybe sorry, graph, I forgot that I wanted to say the definition, that a graph G is said to be k-vertex connected if it has more than k vertices that remains connected after if we delete fewer than k vertices. And the connectivity is denoted by kappa of G, and this is the minimum case such that G is k connected. So if I have this C7, then one can see that this graph is one connected, because if I delete like two vertices, it won't be connected. And what we were able to prove, that the connectivity of k-critical bipartite graph, not necessarily minimal one, so not necessarily even with the minimum number of edges, is the minimum of the minimum degree, which is quite obvious, of course, and k. And now I would like to present the open problems. So the problem one is, I would like to construct the graph such that it has the degrees like ceiling of k or a, or floor of k, a, for any vertex from the set U, and k plus 1 for any vertex from the set V that is not k critical. So that was the open problem that I already mentioned, that we weren't able to find a full characterization of such graphs. So this is still open. And another question is, so if I have a graph G, which is minimum k-critical bipartite graph, so the degree of each vertex from the set V is k plus 1, and we were able only to show the degree of each vertex from the set U is like this. But maybe it can happen that although the maximum degree for any vertex from the set U is the ceiling of this number, but the minimum degree is strictly smaller than the floor of this number. We're able even to find k-critical graphs with such a maximum degree and the minimum one, but it's not like whole family, but it was like one example or so on. So we would like to characterize the minimal k-critical bipartite graph such that the degree of this the vertex is k plus 1 for any v from V, and to find out what is the smallest possible minimum degree from the vertices from U. But remember that you have this assumption. And this is everything what I wanted to say. Thank you very much for the attention.
Thank you, Sylwia, a lot for your very nice talk. Now we can start some questions. Are there any questions? Comments? Remarks? Hania wrote very nice, bravo.
Thank you, Hania.
Mhm.
It was. I have to say that it
Rita?
was strange to say that talk when I don't see the public. Although I used to do that during the pandemic.
Yes, of course.
It's quite strange that I don't see your faces while I'm saying that talk.
Rita wrote, thanks, very nice, but maybe we can have some questions. On Facebook or on YouTube, maybe?
I would maybe comment that for this first problem, even for the second problem, I would like to encourage the students to work on that, because I think that this work has an application really for this robust as nurse assignments. So and I think that it's doable. It's like, probably we are blind because we are using one method, but maybe someone will be more open.
I just like to comment that I like a lot this line version, because in general I am not fast person. And then now we have opportunity to see again the talk, and then we can consider question or comment better later. But thank you.
If no, I think we can say thanks again to Sylvia. Thank you very much for a very nice talk.
Thank
Yes.
you.
Okay, and I think we can have a 5 minutes break, and after 5 minutes we can start with the next contributed talk. Okay.